Hello everyone and welcome to another video. Today I want to continue our series focusing on optimization and look at how we can use optimization techniques to solve a very classical problem in mathematics and engineering, namely solving a system of equations. Now, the discussion today is going to build off several of our previous lectures. In particular, please make sure you've watched the videos covering the penalty method as well as the discussion on F-min search. Now, assuming that you've seen these and you're up to speed, why don't we just go ahead and jump right into it. So the idea with solving a system of equations, right, is that you might have a certain number of equations or relationships, and all of these equations could be functions of multiple variables, and you would like to now solve for a set of variables which make all of those equations consistent, right, or solve them all simultaneously at the same time. So to get our hand on this, you know me, I like to look at concrete examples. So let's just look at an example right off the bat here and get a little idea of how this works. So let's go ahead and consider, how about 3 equations and 3 unknowns? Okay, so let's just write these 3 equations down. Like maybe you've got some arbitrary relations like x1 times x2 has got to equal 3, and x1 plus x2 has got to equal negative 3x3, and x1 over x3, actually, sorry, excuse me, this is x1 squared over x3 is equal to negative 4, right? So here you've got 3 equations, right? Equation 1, 2, and 3, and there's 3 unknowns. I want to know what is the x1, x2, and x3 values, which are going to make all of these consistent or solve them all at the same time, okay? So the first thing we're going to do is let's write this in kind of standard optimization form. Namely, let's move everything to one side and get them all equal to 0. So in other words, I'm just going to translate these into standard form, so we can write this as, let's call the first equation f1 of x, right, which is going to be x1, x2 minus 3 has got to equal 0, right? I think you'll agree I haven't changed anything. This is the first equation. I just move this on the other side, and I'm going to call this relationship here f1. Okay, same thing. Let's do this for the other side. So this is the second equation of f of 2 of x, which is just going to be x1 plus x2 plus 3x3 is equal to 0. And then finally, you got f3 of x is equal to x1 squared all over x3 plus 4 is equal to 0, okay? So these are our 3 standard forms. Let's just number these, how about for giggles? Let's call this equation 1.1, equation 1.2, and equation 1.3, right? Okay, so again, same thing, haven't done anything. I need to solve these 3 equations. So I need to find the vector x, right, which is x1, x2, x3. Find those 3 numbers that make f1 equal to 0, f2 equal to 0, and f3 equal to 0, right? Okay, so how would you go about doing this? Like the traditional way, let's call this the traditional way. Right, you would go ahead and you just start substituting these equations and trying to isolate the variables, right? So for giggles, let's just spend 5 minutes going through this. So let's go ahead and solve equation 1.1 for x1, right? So just take equation 1.1, solve it for x1. What do we end up with? We end up with x1 is equal to 3 over x2, right? I don't know. Let's call this thing, how about equation 1.a? Okay, for an alternative version. Okay, then what we could do here is let's go ahead and sub equation 1.a into equation 1.2. Okay, so I'm going to take this relationship, substitute it into here. What do you end up with? You end up now, well, let's first rewrite equation 1.2, which is just the f2 function, right? So it's x1 plus x2 plus 3x3 is equal to 0. However, x1 is this relationship, right? So substitute that in for x1 right there. And what do we end up with? 3 over x2 plus 3x3 is equal to 0. Okay, you do a little bit of algebra and you can isolate this guy for a relationship for x3 pretty easily. So I'm just going to say dot, dot, dot. You end up with x3 is going to equal negative 3 plus x2 squared all over 3x2, right? Okay, let's call this thing, how about equation 1.b, okay? Now let's jump over maybe to this side of the board. I'll draw a line here so hopefully we don't get confused. Okay, so coming over here, what do we want to do? Now let's go ahead and how about sub equation 1 point A and equation 1 point B into equation 1.3, right? So now focus on this equation. I'll rewrite it again just to make everything consistent. Plus 4 is equal to 0. But now substitute the relationship for x1 right there. Substitute the relationship for x3 into here. And again, do a bunch of algebra and you end up with this. Again, why don't you take my word for it? By the time you make all that substitutions, you end up with this thing. You end up with x2 cubed plus 3x2 minus 27 over 4 has got to equal 0. So great. At this point, you have this cubic, and you just need to solve this for x2, okay? So you could do that graphically, however you like, finding the roots of this polynomial. What you end up with is, again, there's multiple solutions, right? There's 3 solutions for x2. We're going to pick, if you run the numbers, you'll find out that 2 of them are imaginary, 1 of them are real. I think what you end up with the solution set of 1.378-ish, and then there's another possibility at minus 0.68 plus 2.1i, and then you have another solution here at minus 0.68 minus 2.1i. Okay, those are the solutions. Let's just go ahead and pick the real one for our solution here. Okay, so once we have that, we can basically back substitute this into this relationship for x1 and this relationship for x3, and you'd end up with a solution. So in other words, you would say x1 here is 3 all over, what is x2? We said we're choosing this one, right? 1.378. This number comes out to be something like, what was it? 2.18-ish, something like that. X2, again, we said it's right down here, so this is 1.378. And then finally x3, you're going to back substitute this relationship, so it's 3 plus, what is x2? X2 was 1.378 squared. Sorry, what did I, yeah, there we go. Squared this thing all over 3 times 1.378. Right, again, you run these numbers and this thing comes out to, what did this come, oh yeah, here, negative 1.19-ish, something like that, right? So here's one possible solution, right, that solves this. So x1 of 2.18, x2 of 1.378, and then finally an x3 of minus 1.19-ish, something like that, right? That solves it. And, you know, just to double check ourselves, maybe we should, I don't want to run over to Mathematica and break our flow. I'll just flash up a screenshot, how about, of when I plug this into Mathematica, again, you see we get 3 solution sets of this, and the one that is real is actually the one I want to focus on right now, but that basically gives us this exact same solution, right? So nothing is mind-blowing so far. In fact, you might think that I've been wasting your time for the last couple minutes, but what I want to illustrate here is we were able to do this, right? You were able to go through this process and make a substitution and solve this because the underlying equations were somewhat simple, right? These were not complicated, like mega complicated equations, right? But if these were more complicated, this process would probably fail somewhere, right? You'd have real issues trying to isolate variables and solving them. And if you had many equations, that would be even, you know, the problem just gets exponentially worse, right? Mathematica might be able to help you solve this thing symbolically, but again, at some point, it's also going to choke when you're trying to solve these equations exactly, right? So, with that being said, is there another way we could come about and to try to attack this problem, right? Instead of going through this rigmarole of making these substitutions and trying to analytically solve the equations exactly, is there some approximate numerical technique that we can apply that would get us pretty much the same answer, but in a more flexible, I guess, methodology? So this is exactly where we want to now go ahead and apply the penalty method, right? The optimization penalty method. So I'm gonna, again, here's the video on the optimization penalty method. Make sure you've watched this because I'm gonna assume you know everything that's in that video, and we're just gonna jump into turning this set of equations into an optimization problem. So give me a second to pause the camera and erase the board, and we'll be right back. All right, so I've rewritten our three equations, or our system of equations, up here in the upper left of the board, and I've also written the solution that we found analytically, right? So now let's apply the penalty method and see, can I reformulate this into an optimization problem, right? So the optimization problem would be, I need to minimize a cost function such that all of these three are enforced, right? That's what it means to solve a system of equations. They're basically constraints, right? Making sure that we pick an x that satisfies all three of these is the same thing as saying we have three equality constraints here, right? So I need all three of these constraints to be enforced. Okay, so here's kind of an equivalent optimization problem, and if you think about this long enough, you can see that, you know what, this really, solving the system of three equations simultaneously is the same thing as basically finding the feasible set to this optimization problem. So really, the cost function actually doesn't matter right now. If all I'm trying to do is solve these system of equations, all I care about is finding the feasible set. So we should write that down. Solving equations simultaneously is the same as finding the feasible set, right? Feasible set is something that you would understand if you're talking to an optimization person, or solving system of equations simultaneously is if you're talking to just like kind of a general mathematician, but they're the exact same idea, right? So what we can say now is, okay, the cost function doesn't matter in this case. So the easiest thing to do is choose a cost function that's just a constant. Right? And what's a really easy constant? How about a big fat 0, right? So again, the problem here is I don't really actually care about minimizing the cost function. I just care about finding the feasible set. Now, remember in our penalty discussion, right, our lecture where we talked about optimization techniques using the penalty method, we said, instead of trying to call these constraints hard constraints, we were going to shuffle them up to the cost function and then penalize the system via a penalty parameter and a penalty function if these are not enforced, right? If we don't satisfy the constraints. So we should just write that basically we're going to transform this thing via the penalty method to an approximate problem, right? P approx, which was basically minimize an alternative cost function, right? F0 hat of x, right? Which was the original cost function, right? Plus now all of the penalty parameters, like an alpha 1 times the penalty function. So the penalty function for the first equality constraint was basically the first equality constraint squared, right? And then we're going to do the same thing for the other two. Alpha 2 F2 of x squared plus alpha 3 F3 of x squared. Right? And again, you look at this, we said, okay, the cost function was 0, so really I don't care about this. And here we are. So now this problem right here, notice there is no such that, right? We have transformed this constrained optimization problem to an approximately equivalent unconstrained optimization problem down here. So at this point, what we can do is instead of trying to solve those equations simultaneously, I will try to now solve this approximate numerical unconstrained optimization problem here by basically running off to a numerical optimization algorithm and asking it to try to minimize this unconstrained cost function. Okay, so again, I think the best choice for that is let's go over to MATLAB and use fmin search. And again, this is why I'm going to expect that you've probably watched that video on fmin search, so I don't need to go over it. So let's run over to MATLAB, implement this sucker in MATLAB, and have fmin search take a whack at finding a solution. All right, so here we are in MATLAB. Let's go ahead and start with our good old friend clear CLC close all. And now let's go ahead and come up with a guess, I guess, of where we think the solution is going to be. Let's just start off with how about a bunch of zeros is probably as good a place as any. And then what we should do is let's define all of our alpha parameters. I don't know, let's pick 10 for all of them. You know, this is somewhat arbitrary right now. And then what we can do is basically let's make a call to fmin search to see if it can find the solution to our cost function. So I've actually prepared that off screen so you don't have to watch me typing this all in. But again, I'm going to assume that you've watched our video on fmin search talking about how to basically create an anonymous function with extra parameters and call this cost function, which is defined in a separate function. So again, if you haven't seen that or are unfamiliar with what I'm doing here, make sure you've watched our fmin search video first. And all you can see here is we're basically calling fmin search to perform unconstrained numerical optimization on this cost function with the parameters alpha1, alpha2, alpha3. So again, the cost function file is something that I've already again prepared off screen, and it's nothing fancy. It's what you've all seen before. I just basically create the constraint functions here, and then use this to basically build up our cost function, right? The cost function in this case is just the penalty parameters times the penalty functions, right? And that's basically it. So let's go ahead and give this guy a whirl and see what happens. So I'm going to go ahead and hit run. And actually, you know what we should do is let's print out the tell you what, actually I'll just take off the semicolon so we can see what's going on. So, all right, it exited with a 1 here, but if you notice, the cost is nowhere near 0. If it was able to find a solution that could satisfy all 3 of those equations simultaneously, I would expect this cost to be exactly 0, right? That was the whole point of building up that cost function the way we did. So, what we should do here is, you know what, instead of starting at 0, maybe what we should do is let's reinitialize using the last point that it found and start all over. So what I should probably do then is, let's do this. Let me go ahead and up at the top, I'm going to make a flag called initialization, and let's make this 1. So basically, we're going to have 2 ways you can run this. 0 means start from scratch, and 1 means start with last solution. Okay, so what I mean by that here is we can say if initialization equals 0, then we'll start from this location, else xguess is going to be, well, you know what we need to do is we need to come down here at the bottom first, and let's go ahead and save the best solution we've found so far. So basically I'm going to say, all right, go ahead and at the bottom, once you've gone ahead and solved, let's save to a function, or sorry, to a file. Maybe let's call it xstar best.mat, and we'll save the variable xstar. Right? So when we hit line 21 what it's basically going to do is going to take the value that fmin search found, which is this guy over here, which you can see is not the value we're expecting, but it's going to save it into a file called xstarbest. Then the next time we start off, we can basically load that data in here, right? So I'm going to say load xstarbest.mat. Let's load this into some temporary variable, and then we'll extract from that the variable xstar and use that as the initial guess. Does that make sense what's going on? So I know this looks a little bit weird, but basically this is going to allow us, so if we keep this here at 0, this is basically doing the same thing we did earlier. I can just keep hitting F5 on this, and it's going to get the same thing every single time, right? It's going to say, okay, you did not converge, so there's no point in me doing this over and over and over. Instead, what I want to do is I want to solve it one time, get the optimizer to find this solution, then I'm going to flip it over here to the next initialization routine. So I'm going to start now using my last best value as the initial starting point. So in other words, if I run to this breakpoint and hit F10 to execute this, now xguess, you can kind of see that is the value that it solved for last time, right? That was the best solution it found last time. Now I'm going to run it through again with a new guess point and see how the algorithm performs. So if I run this again, look at this. It's a little bit better, right? Now, instead of having a cost of 250, the cost went down to 160. So we got a little bit better, right? And look, this solution is a little bit different, but it's still not the solution we're expecting, right? In fact, we can see right here from the cost that it is not solving the problem. So tell you what, let's keep this like this with an initialization flag of 1 and just keep running through this. So if I run this guy again, look at this. We got the exact same costs. Ooh, boy. And this solution is wandering off to something crazy. If I run this again, Oh boy, look at this. It's still wandering off. Now it's 4,000-ish, you know, or is that 41,000? Oh boy. So, look at this. We are not getting anywhere right here. You see that the cost is still the same, but the optimizer keeps changing the solution, but it still keeps saying that it still violates the constraints. It's not solving this system of equations. So, if you think about what's going on here, the problem is we started this whole process with an initial guess at the origin. Long story short, we've fallen into kind of a local minima in the cost function, and it's not it's not the global minima of the problem. We know the global minima of this problem should be with an f0 of 0. So this initial guess vector was too far away. It was in the wrong location. So let's do this. Let's change the initialization back to start from scratch, but we don't want to use this. So this value leads to a local minima, right? So let's comment this out and instead use something else. I don't know. How about 1 minus 1? Something like that. Let's pick another location, okay? Now if I run this, aha, look at this. The cost is basically 0. So the fmin search algorithm was able to find something, and if you look at this, take a look at that. Those are the exact numbers we want. So what's really powerful about this is, if you notice, we didn't have to do any crazy substitutions or symbolic manipulations or anything like that, right? We basically let the numerical optimization scheme run, and it found a solution which makes all of the equations consistent. So long story short, we solved those systems of 3 equations for 3 unknowns with basically a numerical optimization routine. So, the only thing that we had to note here was that you needed a little bit of information about where is a good starting point in order to allow the optimizer to converge to the solution that we were looking for. So, that being said, let's talk about something interesting. Let's jump over to the board, and I want to stick with this problem just a little bit longer. All right, so that was pretty neat that we saw that we could basically solve this system of 3 equations for 3 unknowns, right? And we said these were sort of the optimal values. Maybe we should put the little star on this to denote that that's what the optimizer also came out with as the optimal solution by basically applying this penalty method we talked about earlier. Now, what's really cool about the optimization approach is that, let's revisit our system of equations, right? We said those are 3 equations, 3 unknowns. We saw that there was a family of solutions. What if the problem was over-constrained, right? Right now, you can almost think of the problem as being kind of fully constrained, right? There's 3 equations, 3 unknowns. You don't have an infinite space of solutions, right? In fact, I think we saw there were only 3 solutions here. What if we over-constrained it? Like, what if we added a 4th constraint? How about f4 of x is something like, how about x1 minus x2 is equal to 0, right? And if you think about what this 4th constraint says, it says x1 has got to equal x2, right? That's what it says, which basically makes this inconsistent. So this will not solve this system of equations. In fact, the problem right now is it's over-constrained. In fact, you won't be able to find a solution to this analytically. In fact, here's a screenshot of Mathematica choking on this right now. If you give it these 4 equations, ask it to solve it for 3 unknowns, it just throws up its hands and says, forget this, right? There's no solution. Now, you could be stuck there. Or, you know what might be interesting is, let's do a little experiment. Let's say that, you know, this is the solution we got if you used F1, 2, and 3, right? If those were active. So you get this solution, right? If you use F1, F2, and F3, right? That's without F4. Okay. Now, what happens if we throw away one of these equations here in our over-constrained problem? For example, let's say you axe this first one. If you get rid of F1 and then try to solve these 3 equations, basically F2, F3, and F4, you'll also get, it becomes feasible again, right? So what you could also get is, maybe let's write this down here, and then we're going to go see this in a second, but you could also get x1 star, x2 star, and x3 star. You would get different values. So again, if these bottom 3 constraints are active, obviously x1 has to equal x2. The solution you get here, I think, is 2.67, 2.67, and then 1.78. Okay, and again, this is a solution you get if F2, F3, and F4 are active, right? So, okay, let's go back now and say, what happens if all four of these are active? Okay? If all four are active, there's no solution to the problem, but we can still go ahead and try to formulate this penalty or the approximate optimization problem via the penalty method by basically just, again, the full problem is now this, right? That's the full problem, and now we're going to transform it into an approximate problem via the penalty method, so all we got to do is tack on a fourth alpha 4 f4x squared, right? And now what we can do is, by varying the values of alpha 1, 2, 3, 4, by varying the penalty parameters, we're almost coaxing the optimizer into saying which one of these constraints are, or which one of these equations are more important to solve, right? So for example, you know what might be an interesting study to do? Let's use this mapping here. How about let's use a mapping of, how about alpha 1, let's make this 1 minus beta. How about alpha 2 is equal to 1, alpha 3 is equal to 1, and alpha 4, let's make this thing beta. So what this cost function becomes, right, is we said alpha 1, this is 1 minus beta, right? We don't have an alpha 2, we don't have an alpha 3, and then alpha 4 is just beta, right? Okay, so if you look at this cost function here, what's interesting here is if beta is equal to 0, right, what happens? Beta is equal to 0, we basically, now only F1, F2, and F3 become constant, right? Because if beta is 0, it basically says there's no cost for failing to or for failing to activate or for failing to satisfy constraint F4, right? So this basically reverts or becomes scenario 1, right? So we expect that if you use a beta value of 1 to solve this, you would get this solution here, right? And similarly, if beta is equal to 1, this becomes scenario 2, right? So let's go over to MATLAB now and vary, how about this beta parameter between 0 and 1, and see what does the optimizer do when you try to solve this, right? So we see that when beta is equal to 0, it should basically act like this condition where we get that solution. And then when beta is equal to 1, it should act like this solution. And now the question is, what does it do in between, right? Is it still able to find solutions, or I guess it's going to find a number? We should ask, is that an actual solution or not? So let's jump over to MATLAB and do this real quick. We'll implement from beta going from 0 to 1 in the similar fashion that we just did. All right, so we're back here at our MATLAB terminal. So let's just go ahead and make some of those changes that we talked about. So let's go ahead and rewrite our cost function. So now it's just going to be a function of beta. And now what we've got is we have an F4. And what did we say F4 was? F4 is just x1 minus x2. Something like that. And I think we said this is now what it was this 1 minus beta? I think this was a 1 minus beta term. And then alpha 2, this was just a 1, and then this was just a 1, and then we have to tack on the beta times f4 squared. Okay, so we've modified our cost function appropriately to take into account that fourth constraint. So let's go back to our solution method. And you know what? I don't think we need this initialization anymore. Let's go ahead and maybe take all this out. Because we saw that if you start at this location, this leads to a good solution on the first try. So I think we can get rid of some of this just to make our lives a little bit easier. And for now, let's go ahead and use, again, what did we say? We said when beta was 0, we should revert to the exact same solution that we saw earlier. So let's go ahead. I'll delete some of this, clean it up, make it a little bit easier. Oh, I think we have to change this. This is now no longer alpha. This is now beta. Right? Okay, so I think if we run this guy... again, yep, there's 0 cost there, and yes, I think that is exactly what we're looking for, right? So we said when beta is equal to 0, we end up with that same solution, and now, if beta is equal to 1, now what we're doing is we're saying, instead of obeying that first constraint, we're going to throw away the first constraint, and then now enforce the fourth constraint. So if I run this again, look at this. Again, we get a very good solution, right? The cost is 0, so we're satisfying all the constraints as appropriate to the penalty parameters that we've input. And now here's that solution that we talked about, right? 2.67, 2.67, and negative 1.78. So what would be now interesting, though, is now let's just go ahead and make a little bit of data so that beta is changing every round. So let's make a vector. Let's call it beta data. How about lengths? We'll make it go from 0 to 1, and maybe let's do this in 20 iterations. And then let's just wrap this in a for loop. So how about for k gets 1 to length of beta data. Whoops, sorry. Data. Wrap this guy like that. Let's go ahead, select all this, and smart indent it. So there. Oh, and beta now is actually going to be beta data sub k. So we're just going to vary beta as we go along. And you know what we should probably do? Let's go ahead and save the x star data that we get. So I'm going to initialize an empty container for all the values of x star that we're going to save through this loop. Let's do the same thing for the cost function data. Let's initialize an empty container. And then what we're going to do is let's go ahead and first, we're just going to go ahead now say save the solution at the current beta value, right? So x star data, all rows, column n plus 1 is going to get the current value of x star, of the current optimal. And same thing for the f0 information. Let's do something very similar where we basically save the current value. The last thing maybe we should do is every time through this loop, let's just make sure that the optimizer, aka fmin search, converged to a solution. So maybe let's just go ahead and assert that the exit flag is equal to 1. Okay? So if we rip through this, what we should be doing is we're going to vary beta from 0 to 1 and basically solve this thing 20 times and see what we get. So again, if I run this guy, yep, okay, it looks like it's solved. Everything went through, no problem. Let's now go ahead and just plot the progression. So to save time, I've actually prepared that off screen. I'll go ahead and just paste it in here, and we'll talk through exactly what I'm doing. So all I'm doing here is first, let's go ahead and plot the starting point. So this is the first solution here. I'm going to plot this in 3 space, so I'm using plot 3. This is the solution when beta is equal to 0. Then I'm going to plot the endpoint, right? This is the solution when beta is equal to 1. So I'm going to plot the first one with a red circle, then I'm going to plot it with a red X, and then I'm going to just draw the progression as beta varies from 0 to 1 using a line here. And then down here in a completely separate figure, let's plot what does the cost function data look like as we vary beta. So again, if I just run this script, hopefully what we should get, let me grab and drag it over here. Here's the first figure. So this, if you look at, is basically the progression of we started, here's the beta equal to 0 location in x1, x2, x3 space, right? And as we start varying beta, you see that the solution, it doesn't vary necessarily in a straight line, right? The optimizer is trying to satisfy all those constraints. So everything along the blue line, right? If you're not at one of these 2 endpoints, the optimizer is not actually able to find a complete solution. And we can see that evidence by if we look at the cost function value here. So the cost here at beta equals 0 is 0. So we are confident that the optimizer is able to satisfy all the constraints simultaneously, which made sense because that was the case where we actually only had 3 of the constraints active. But the second you actually start increasing that beta term, somewhere between 0 and 1, we see that the optimizer it converges to a solution, but that solution is not able to solve the over-constrained problem, right? So this is almost a value or a measure of how much are those constraints or those equations being violated at the optimal location, right? We have a solution, right? The optimizer kicks out a value of x1, x2, x3 at all those locations, but this is effectively telling us how bad is that solution or how far off from solving all 4 of those equations simultaneously is it. So we see that, it's non-trivial. All right. The thing that is beneficial about this approach is if you think about this, right, at least the optimizer didn't do what Mathematica did and didn't just throw up its hands and say, there's no way you're solving these. I'm not even going to try, right? What the optimizer did is it tried to find a solution. It did the best it could. And here, this is the evidence, right? This line here in x1, x2, x3 space is the optimizer's best guess or best attempt at solving all four as close as it could get, right? And it gives you actually a measure of how far off it was or how bad it was at solving them. So this is better than nothing, right? We know that the solutions along these lines don't satisfy the equations, but we can have an understanding of how poor the solution is, right? So if you're in a situation where really it might be okay to fudge, or if some of those equations don't all have to be satisfied at the same time, maybe it's okay. Maybe as long as the value is below a certain F0 value, if the cost is below a certain amount, you'll tolerate it, right? So again, I just wanted to show this because I think the penalty method and using numerical optimization to try to solve an over-constrained problem is actually can still be useful. Even if it can't solve it, it can still provide some interesting results. So, with that being said, let's jump back over to the board and maybe talk about inequality relationships now. All right, let's see now if we can apply this to solving both equalities and inequalities as well. So inequalities are another set of constraints, right, that you might be able to handle with this penalty method. So again, let's look at an example here. So I'm going to come up with, let's come up with 5 equations or 5 relationships in 6 variables. So here's x1, x5 minus 3 is got equal to 0, and then x1 plus x2 plus 3x4 is equal to 0, and then how about x2 squared all over x6 plus 4 is equal to 0. And then let's put in some inequality constraints. How about x1 plus cosine of x2 times x5 is less than or equal to 0. And then finally, how about an x5 plus x1 plus x3 plus 7x6 is less than or equal to 0, okay? So this here is f1 of x, and then f2 of x, f3 of x, f4 of x, and then finally an f5 of x. So you see we've got 5 relationships in 6 unknowns, right? x1, 2, 3, 4, 5, 6, right? So again, solving this analytically, right, it's an under-constrained problem, so hopefully if all of these are kind of, at least none of them are inconsistent, we should be able to find an infinite number of solutions for this. Now again, that is kind of intractable to do by hand, right? It's not going to be a lot of fun to do this by hand, especially with these inequality constraints in play. But what we can do is we can go ahead and convert this again to a approximate numerical unconstrained optimization problem, which we can then throw at a numerical scheme. So again, what we're trying to do now is minimize our F0 hat, right? Which in this case was going to be what? We have alpha 1 f1 of x squared plus alpha 2 f2 of x squared plus alpha 3 f3 of x squared. So this was the penalty parameters and penalty functions for all the equality, right, relationships. Oops, sorry, nope, I did draw that at the right spot, that's right. So these are for the equality constraints. And then we have to add on an alpha 4, right, times the penalty function for the inequality, right? We said that the proper one, or a popular one to use for that, is basically the maximum of 0 and f4 of x. And then outside of the maximum, we square that thing, right? Plus alpha 5 times the max function of 0 times f5 of x, and then square the outside of that, right? So here were the penalty parameters and penalty functions for the inequalities relationships, right? So there we go. We basically now, let's run over to MATLAB again and throw fmin search at this slightly different problem and see if it's able to find us a solution which will satisfy all 5 of these relationships simultaneously. All right, so here we are back in MATLAB. I've prepared the script. Again, this is exactly like what we looked at earlier. The only difference here is now that we have 6 variables. Our initial guess has to be a 6x1 vector. So again, we can either start from scratch by just initializing with a guess of, in this case, again, all zeros. I guess we'll see how we do this time with this starting point. Or you can load in your last value and try it over. Again, also to make our lives easier, I'm just going to make one vector of alphas instead of having an alpha alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, alpha 6. I'm just going to, alpha 5. I'm just going to collect them into this one 5 by 1 vector alpha and then pass that into our cost function as a single extra parameter. Let's take a look at the cost function and we'll see, again, nothing fancy about this. Again, we have our equality constraints and then we have our inequality constraints. And then all we do is we build up the cost function with the penalty parameters and penalty functions for the equality constraints, and then the penalty parameters and penalty functions for the inequality constraints. So, with that being said, let's just give this guy a rip and see how we do. So I'm going to run this guy. It converged to a solution, but if you look at the cost, it's not 0, so we did not satisfy all of the constraints on the first go. So let's go ahead and flip this bit to a 1. And load in our last values and start the process again from this location. So I'm going to start this again, and aha, there we go. That sure looks like a 0 to me. So this solution that it found theoretically should satisfy all the constraints. And actually, you know what we should do just to make our, for completeness, let's go ahead and I'm going to paste a little bit of code down here. That is basically, let's just check that we satisfy the constraint. So basically, let's just go ahead and plug in the x star value that we get into our function f1, f2, f3. All of these lines should evaluate to pretty much exactly 0, right? And then for f4 and f5, these things, they just have to be less than 0, right? So if I go ahead and basically evaluate this entire section, let's see what we end up with. And here we go. Look at this. This looks beautiful. Look, F1, F2, F3, those are all pretty darn close to 0. So we satisfy the equality constraints. And then the solution that we obtain also, look at these. These are very well negative. So again, we satisfy the inequality constraints also. So this solution that the optimizer found, it satisfies, or it solved 5, I guess I can't call them equations, right? It solved 3 equations and 2 inequalities. So it solved 5 relationships total for 6 parameters, right? So again, this is pretty darn cool because it found us a solution. And maybe we should say that. The one potential drawback with this is we didn't find the family of all possible solutions, right? The optimizer is just going to find a solution for you, one that satisfies all the constraints. If we were to change our initial guess vector, we might find a different solution. You know, I mean, heck, why don't we try that for giggles? Let's go ahead, comment this out. Let's try this whole process again with another set of guesses. I don't know. How about a 1, 2, 3, 4, 5, 6? Right? So let's go ahead. Maybe what we should do is let's take a screenshot of this value. Okay, I'm going to put this in Paint just so we can save the values that we had earlier. Okay, so I'll just paste that into Paint. Okay, and now let's go ahead and run this process again. So we're going to start from scratch. Let's go and run this guy. And what do we end up with? Oh, actually, gosh, look at, wait, no, where's our F0? Yeah, look at this. On the very first shebang, we got a solution here, right? This is basically 0. And let's check our constraints. Yep, F1, F2, F3, those are all 0. F4 and F5, those are, yep, well clear, well negative. So again, this solution right here also satisfies those 5 relationships, and if we compare it with what we got earlier, we get a very different number. So again, what this is going to do is it's not going to be able to find us all the solutions, right? But it's a very robust, easy way to find one solution, right? So with that being said, I know the discussion today seemed a little bit kind of abstract because we were just looking at these arbitrary equations, but if you stick with us, in fact, if you watch our very next video, we are going to apply this method now to solve a very real engineering problem. So we're going to try to take an airplane, and I want to trim that airplane for a certain flight condition. Like if I want to fly an airplane straight and level at a certain speed, we can actually use this exact method we just covered right now to try to find what are the appropriate control surface deflections and what state does the aircraft have to be in order to achieve that condition. So I hope you'll join us at our next video. That being said, I think this is a great spot to leave it. I hope you enjoyed the discussion today, and if so, I also hope you'll consider subscribing to the channel. If you just scroll a little ways down, hit that subscribe button. It really does help me continue making these videos. Also, please let me know what you think about this video, or if you'd like to see other topics in the future, just leave a note in the comments. I think it's a great way to have some discussion going amongst like-minded individuals on this topic or other engineering or mathematics topics. So, I hope to catch you at one of these future videos, and until I see you then, I think I'll sign off for now. Talk to you later. Bye.